Hello everybody, welcome to our video series on Spur gear design. So what we're going to do today is actually do a quick example from the Robert Mott book. So basically the book is Machine Elements in Mechanical Design, 5th edition. I have the title in the description and later in the slides. Let's quickly recall the different steps that are involved. So basically what we're going to do is do like a really simple example of a gear design. So this is kind of how you do it manually. The one with the book, there is actually a companion CD which is kind of significantly easier. So if you did purchase the book, kind of install the CD, but unfortunately if you're taking the exam, you would have to do it manually. So it's a good idea to know how this comes about and then kind of like double check your numbers as well. Okay, so let's recall the steps. So this was kind of a continuing with the previous video, so they're slightly modified. So the first step is basically you'll be given the power and the speed. So this is basically you'll be your application. So if you are kind of designing everything from scratch, so for instance, if you're designing a motorcycle engine, you need to have some idea about what is the power that's needed. So that kind of comes from outside the scope of this design problem itself. But we're going to assume at this point that you know the power in horsepower. As I mentioned, we're going to be using imperial units and the speed in RPM. So once you have this, we can do the different design. So what we do is we're going to pick the pressure angle, which is typically 20 degrees. And then we need to make sure in our design that we have a minimum of 17 teeth and a maximum of 150 teeth. So the minimum 17 teeth comes from our desire to avoid interference in our links. So the next step is we're going to pick a material. We're going to be picking steel because that's the one that's most commonly used and there are a lot of data available. You can certainly follow these steps. So to basically do the bronze gear design, just that there will be small modification that you would have to figure out what the initial trial pitch would be and how do you come back and actually select the material in terms of the hardness and so on. So once we have the material fixed, we're going to figure out what the overload factor is. So this is useful in this book, at least in the initial step where we can identify the overload factor and then use that to get a trial pitch. So the overload factor is in table 9.7 in the 5th edition of the book. So once you have that, we're going to specify a trial pitch. So for that, what we're going to do is calculate a desired power. So the desired power is a product of the overload factor and the input power. So the overload factor basically comes about because when you're engaging different machines, so based on the input, so if it's an electric motor, it's going to be fairly smooth. IC engine, so if it has very few cylinders, like 2 cylinders or single cylinder, that has a lot of shock. So based on that, the effective load that's transmitted, even though the average might be say 100 watts or say 50 horsepower, the actual load might be like cycling over and over. So this will actually create additional stresses in the gear. So we need to take that into account when we're doing the design. So using these two, what we can actually do is actually use figure 924, which is 927 in the old book. And then we can actually calculate the pinion desired speed. So let's quickly go to that slide here. So this So this here kind of shows you the different, okay, so this is figure 924. So this here basically shows you the different pinion diameters. Basically, if you look at the bottom over here, so this gives you, oops. Okay, so this is figure 924. So if you look at this, at the bottom of the screen, you have the pinion diameter. And then here it's going to be the desired power, which needs to be the product, if you notice, of the KO, which is the overload factor, and the power needed. And if you look at these graphs over here, all of these basically have the diameter of the pitch, the diametral pitch, and then it tells you what is the diameter of the pinion and so on. And also this can also be used to calculate the metric module of a gear. So the point to note here is this is basically numbers for some fixed value of diameter. So this is kind of what is basically done is you can, like when you basically fix the diameter, you can actually go ahead and then calculate the amount of power that can be transmitted based on the forces that will be involved. So once you do that, so you can basically plot this for different, like, so this is essentially like a fixed number of teeth and you keep increasing. So if you look at this, you will notice that the PD, the diametral pitch, actually decreases from one to the other. So the bottom one is 32, 24, 16, and so on. If you recall from our discussion, the diametral pitch is kind of related inversely to the size of the teeth. So essentially, if you have a smaller diametral pitch, you're essentially making your gears larger or making the gears stronger. So what will happen is when you do this calculation, and you'll also notice that the power here, the desired power also increases as the diametral pitch decreases. So what will basically happen is you'll kind of have a calculation of desired power. So if it's say 7 and then your RPM is 1800, they basically intersect at this point, and then you say, okay, you know what, I can pick one of the diametral pitch. I can either pick the lower value here 16 or that higher value here 12. So always keep in mind that these lines are actually the limits. So if you are here, you should kind of pick the one on the higher side. So you're going to pick 12 in this case. So that's the point to remember, because if you end up picking a very small or rather very large diametral pitch, what will happen is when you do the calculation, you would require an insanely large amount of strength on your gears, which will not be possible. So you would have to kind of go back and calculate. So make sure you always kind of pick the smaller diametral pitch or basically go to the higher line over here. Again, these are only kind of the initial values. If you're doing like some intense gear design, you might have to go back and select and look at these numbers. Okay, so coming back, so we did this. Next, what we do is once we have the diametral pitch, we've already designed the number of teeth, we can actually calculate the center distance and calculate the face width. So typically we choose the face width as 12 over PD, which is the nominal face width. After that, we're going to calculate the different K factors. So for these, you would look at table 9.8 and then figures, this should be 9.16 and 17. So this is 9-16. And 16-17, and then this is 9.18 and so on respectively. So this is the next step. Once you have this, you're going to use what's known as calculate the number of cycles. So this is the total number of cycles for which you want the gear to last. So this is a really straightforward formula. We discussed this before. Here L is going to be the lifetime of the gear that you would expect. So this comes from table 912. So these numbers kind of give you an idea of how long typically you want the machine to last. Then you kind of choose the number of the RPM and Q. So if you multiply all of these and then multiply by 60 because of the conversion from minutes to hours, you get the total number of cycles. Then we determine the factors Ji, which are the geometric factors for J is a geometric factor for bending, I is a geometric factor for pitting or contact resistance, and then you similarly have the Yn and Zn, which are the cyclic factors, and then you would basically refer to these in figures 15, 21, 20, and 23 respectively. Next step, we're actually going to calculate kind of what is the material that we can choose in terms of ST transpose, which is going to be the equivalent bending stress, and then SC prime, which is going to be the contact stress. So we typically do these calculations for the pinion. The loads itself is going to be similar because we are mainly concerned about the height of the teeth, which is going to be the same between the two gears, as well as a contact. Just the curvatures might be a little bit different. So if we look at this, the load for the pinion, we basically calculate the load. Again, if you recall, this kind of the weird number comes in because of our conversion from the imperial units conversion from one unit to the other. And then once you have that, WT is the tangential load. Once you have that, we basically have the service factor over here, K as a reliability factor. Typically, you assume these two numbers to be 1. unless otherwise specified. So once you have these two, yn f is the phase width that we calculated before, j, all of these other parameters basically have been already calculated. And then we also calculate sc prime. Similarly, basically using a different formula. So Cp is the elastic modulus, or rather the effective modulus. And then for steel with steel, basically you use 2300. The unit is psi to the 1/2. Right, so once you have this, you can actually calculate all of the loads, and then once you have the loads, you can basically calculate the material that you would select. So the material selection is kind of straightforward. So particularly if you're using steel. So once you have the ST prime and SC prime, you're going to go check figures 911 and 912. The ones 910 and 911 are in the 4th edition of the book. So from these figures, you can actually look at or determine an acceptable value of hardness, and then use this hardness to basically calculate the material that you get potentially used. So let's quickly look at figures 911. So if we look at this, you have the Brinell hardness number over here. And then here is this one is for the allowable bending stress. So this is SAT. So what you do is you typically pick grade 1. It's kind of weaker material. So grade 2 is more expensive, so you need more processing. So you're going to pick always the lower line, grade 1. So what will typically happen is you'll do some calculation, and then this is basically in kilo PSI. So this is basically so this is pounds per square inch, and then this is actually the product up by 1000, so this is actually kilo PSI. So let's say you do the calculation, and then you say, hey, you know what, I get a number of 40 kilo PSI, kPSI, or 40,000 pounds per square inch. So what I'm going to do is kind of take this line over here, and then since I'm going to be picking grade 1, so this is my point, and then I'm going to go down, and then I'm going to say I'm going to look for a Brinell hardness number of 350. So once you have this, you typically look at your appendix. So this is going to give you the Brinell hardness number based on the bending alone. So you're going to go back. So what will happen is you look at the next figure, 912, which is the hardness for the contact. So this contact for the pinion is typically the limiting case. So imagine you basically do the calculation, and this number comes to 150. So you kind of do this again. Again, we're going to pick grade 1. So and then go down here. So this let's comes to 375, right about here. So you basically say, okay, I got a 375 here, and the previous hardness, I don't recall, let's say was 300. Then we basically going to go back and say, look at the table and say, hey, I want to pick a harder material which will satisfy both the contact and the bending requirement. So this is figure in appendix 4, which this is for one of the materials. This is basically giving you the elongation and different parameters, but what we'll basically end up doing is basically just look at the bottom alone, because we know the material, and then I'm going to say, okay, let's say you needed hardness number of, we did say 400, so this is basically going to be between say 429 and 388. Basically you can linearly interpolate, or just to be safe, pick the harder number with the lower temperature of quenching. So in this case, you can basically either say you're going to go with 800 or you're going to pay 850. So once you have that, you're going to default your material. That's fairly straightforward. Okay, so now let's proceed to the actual problem itself. So this is from the Machine Elements in Mechanical Design 5th edition, Robert L. Mott. So this is problem 94, excuse me. So this is a statement of the problem. So design a pair of spur gears for a chipper where intermittent use is expected, and 3 horsepower 1750 RPM electric motor is used, and then it needs to drive the output at a speed of 460 to 465. Right, so this is a problem. So this, as we recall from the steps, is not that difficult, though, at least the first step. So the first step, what we're going to do is actually design the gear train of this problem. So step one, you design the gear train. So here NP over NG is little NP and NG are the RPM. So what you're going to do is basically shoot right in the middle and then basically use a number of 462.5. This gives us a reduction ratio of 3.784. What we can do is get 17 teeth, calculate approximately what the number of teeth would be for the gear. So we do the calculation, it comes to 17 teeth with 64.32, which is basically rounded down to 64 teeth. So that gives us an output speed of 464.84 RPM. The other calculation is if you took 18 teeth, so you basically get the output speed of 463.24. So we're going to pick 18 teeth. So this gives us P is 18 and NG is 68. So this is closer to the middle. Next, what you're going to do is for our application, we're going to look at table 9.3 to get the AGMA numbers for the particular application. So let's quickly look at this table here. So we're going to look at table 9.3. So we will use table 9.3 to get the AGMA numbers. So this basically comes out to, you can use either A11 or A10. So the book basically uses A11, but then we're going to basically use A10. So we're going to assume we're going to be using steel gears. So here's step 3. So we're going to calculate KO, which is the overload factor. So for this, we're going to use table 9.7. So let's go to table 9.7. So we basically had a smooth input, basically. So we're going to use uniform power source, and then the driven machine was basically heavy input. So that basically gives us a factor of 1.75. That's over here. Right. So we're going to use this back in our calculation. Put this back. So let's calculate. So for KO is 1.75, and then we can use this in our next step to calculate the trial pitch. So to calculate trial pitch, we first need to calculate the desired power, which is going to be KO times the input power. So that becomes 1.75 times 3, which gives us 5.25 horsepower. Keep in mind, this is actually the input is at 1750 RPM. So we're going to use figure 924. So that's coming up here. So recall, we're going to basically look at this figure. So we have an input power of 5.25 horsepower. So that's over here. So this is 5, this is 7. So this is, keep in mind, this is actually in log scale. So basically this is kind of somewhere here between 5 and this is going to be 6. So 5.25 is going to be somewhere over here. And then look at our RPM. So the RPM is 1750. So this is 1800. So this is 1800. And then we have 5.25 0.25 over here, a little over 5. So we get the point somewhere over here. Keep in mind, as I said before, we're always going to use the higher values. So in this case, we're going to choose PD, the diameter pitch, equal to 12. So that's the diameter pitch. So we use figure 924. We did that, just show that in the previous step. And then we can basically calculate the diameter pitch to be 12. So once you have the diameter pitch, you can actually calculate the face width, the nominal face width at least. So that's going to be 12 divided by PD. So, and we can calculate the diameter of the pinion, which might be required at a later step. So this is basically the n number of teeth, which is 18 divided by 12 PD. So that gives us 1.5. So 18 by 12 is 1.5. So then we calculate the center distance. So center distance is the sum of the two diameters by 2, which can also be written as number of teeth in the pinion plus number of teeth in the gear, the whole thing divided by 2 times the diameter pitch. So this comes to 3.588. Keep in mind, we want to specify this to 3 to 4 decimal places, so do not use the preferred dimension. So keep in mind that you do not round this. Proceeding to step 6, we're going to calculate all the K values. Ks, looking at table 9.8, is going to be 1. Kb is going to be 1, assuming it's a solid gear. Then we're going to calculate Kn. So for Kn, we're going to find Pf is 0.42 and then Cma is 2.64. So you can either use the formula for this, or you can basically use the so keep in mind that you can either use the formula for this, or you can basically use figures 16 and 17. So they're basically based on the face width over here. Both this uses face width, both of them. And then you can use this, calculate, basically go up face width, and then you know F over dP, and then figure out what these values are. Or it might sometimes be easier just to use these formulas over here. We're going to assume open gears, and then that makes our life a little bit easier. So once you have this, the formula for Km is basically 1 plus Cpf plus Cma. So that basically becomes 1.306, or we can just simply use it as 1.31. So continuing with step 6. So we have Kv, which is the velocity factor. For this, we need to calculate the pitch speed, which is given by pi times the RPM of the pinion times the radius diameter of the pinion divided by 12. So this comes to 687 feet per minute. The next thing we do, so this is basically like pi d by pi, it's actually the formula is pi d times n, but because of the conversion from inches to feet, you have to divide by 12. So once you have this, you're going to use figure 20. Keep in mind that we had an AV of 10. So we're going to use figure 920. So bring that back in. So we had an AV of 10. So we're going to pick this as AV is 10. So pitch speed that we calculated was 687. So this is 200,000 is over here, so 500 is somewhere over here, so kind of go up. So this will be 500. You kind of go up here as smoothly as possible, and then this is 10, so I'm not very straight over here, so that comes to somewhere over here, right? So that's my point. Basically, sorry, this is 10, so this comes to 1 point. So if I did the line correctly, so it should basically meet here, so I'm going to pick 1.35. So proceeding to the next step, which is going to be calculating the load. Before that, we're going to calculate, sorry, the next step is going to be calculating all the factors. So step 7 is to get the value of L from table 912. So if you look at the table, for this particular application, it recommends 3000 to 6000 hours. So let's look at table 912. So for this particular application, it recommends basically this in agricultural equipment. So this basically recommends about 3000 to 6000 hours. So what we're going to do is basically pick something in the middle. We're going to use 4500 hours. The book uses 3000 hours. So this is kind of application dependent and also left to the discretion of the designer. So if you choose smaller number of hours, it's likely to fail quicker. If you choose larger number of hours, you'll basically make the design more expensive. So the value for the number of cycles, NC, is given by Q times L times NP, which comes to 3.15 10 to the 8 cycles. Next, we're going to calculate the values for I, J, Yn, and Zn. So I comes from figure 9.21. So let's look at that. Figure 921. So this is factor I. So we had the gear ratio that was about 3.7 something. So it was 3.784. And then we have the number of mating teeth that we calculated was 68. So this gear ratio is 3.78. So 3.5. And then somewhere over here. Somewhere over here, 3.8 somewhere over here, and then the match teeth on the other gear was basically 68. So this is basically 24, 30, and 50. So it's basically going to be somewhere in the middle over here. So we're going to basically linearly interpolate. So basically here, like basically here to here, we're going to basically linearly interpolate. So basically this is somewhere over here, and then we can basically calculate this number, which comes to about 0.105 basically. So we're going to calculate the value of I from figure 9.21. So let's look that up. So this is figure 9.21. So basically we're going to look at the number of teeth in the pinion was basically 18. So basically this is 16 teeth in the pinion. This is 24. So we're going to basically linearly interpolate between these values. The other thing we needed was basically the excuse me, the gear ratio that was about 3.787 something. So that basically is about 3.8. So this is 3, and then notice the number of divisions. Basically there's 1, 2, 3, 4, 5 divisions. So basically each unit is 2. So we're going to basically be about here. So we're going to go up. So basically between here and here, we're going to kind of linearly interpolate between these two numbers. So that basically comes to somewhere over here. Right, and then kind of go figure out what this value is going to be. So this comes to 0.105. So the next value we're going to calculate is calculate J. This comes from figure 915. So this one is slightly more complicated. So this, I only have the figure for 20-degree pressure angle. So for this, the number of teeth in the pinion is important again. So this is 17, 18, 19. So basically we had 18 teeth. So we're going to pick this line. And the number of teeth in the matching gear, so that basically was 36. Sorry, then, and we're going to pick the number of teeth in the matching gear, so that was 68. So basically we're going to pick 68 here. So this is 50 and then this is 85. So basically we're doing these two lines and then kind of go up. So this is basically kind of the calculation here. So you're going to get somewhere over here, and then that number comes to 0.32. So basically it's come kind of over here, right? So you kind of figure this out and then kind of look up this number over here. So that comes to 0.32. So next we calculate yn and zn. So yn comes from figure 922 and zn comes from figure 923. So let's take a quick look here. So this I scanned from an older version of the book, I realized. So the newer version doesn't have, so I had kind of like blacked out some of the stuff. So for yn, what we need is we had 3 10 to the 5 cycles. So we are looking mainly at the pinion. So 10 to the 8 is over here, 3 10 to the 8 is over here. You kind of go up, figure this value, and then this is somewhere in the middle of 1 and 0.9. So we're going to take yn is 0.95. Similarly, we look at the table for zn, which looks fairly straightforward as well. So it's going to be 10 to the 8, 1, 2, 3, 10 to the 8. Kind of go over here, kind of go back, and then if you look at the calculation, so this comes to about 0.92. So again, if you're doing it in the exam, so we'll be okay with either 0.92 or 0.95 or 0.9, as long as you don't pick 0.6 or something. So it needs to be reasonably close to what the values are. So that's that. So we have all the requirements. The next thing is we were actually going to calculate the stresses. So for this, the first step is we're going to calculate the loads. So yt, wt, if you recall, this looks kind of weird. So it's 126000 times p divided by nd. Again, this is because of the conversion going in the imperial units, things get a little messy. So once you have this, you can calculate the load to be 144 pounds. We use Cp is 2300, and then we can calculate St prime and Sc prime. So St prime is 17.59 kilopascals, kilo psi, excuse me. Sc prime is 136.6 kilo psi. So notice that the Sc prime is much larger, the contact stress is larger than the St prime. So next we're going to look at figure 911 and 912 to get the value of H, the hardness value. So let's look at, pull that figure here. So figure 911, that's here. So we are looking, if you recall, we are looking at St prime of 17.59. So let's look again, this is kilo, so this is 20, and you notice that it's not even on the scale, so you're not really concerned about this hardness. The contact stress, which is in the next figure, is 136.6. So let's look at this. It's 100, 125. Between here is going to be 137.5. So that's thereabouts. So we kind of pull this, figure out what the hardness number would be. The easier way to do it would basically be just to plug it into this equation over here. If you do that, we can get the calculation. We get 333.85, or you can basically look at this and then you'll get it at about 335 or something somewhere over here. Again, the lines aren't very straight, but if you do the calculation, you'll find it somewhere over here, and then you can use that to calculate the HB that you need. So the HP comes to 333.85 either using the figure or the formula. So this is based on, actually if you recall, this is actually based on the contact hardness because that is the limiting case. Once you have that, we're going to pick a material. So we're going to choose 4140 for the gears. And then we're going to look at the appendix figure A4. So let's pull that up here. So we wanted a hardness of 333.85. Keep in mind we're going to look at the bottom over here to kind of relate the hardness to the temperature. So the hardness we wanted was 333. 300 is you're going to basically be going over here. So this is 340. So it's basically between 341 and 310. So what you're going to do is basically 333, right? So it's 341 is a good enough hardness, which is actually more than what we need. So we're going to basically pick somewhere over here or over here. So that gives us, like if we want it to be safe, we can actually go one step further, pick 900, but we are basically comfortable with basically a oil quenching temperature of 1000. So we can basically use either 900, or we are actually more comfortable using, or this thing can also be 1000 basically. Right, so both of them are acceptable based on the figures that we get. So this basically concludes our design on gear. So this is a very simple example. You can basically repeat the same procedure. In metric gear it will be slightly different. You can use similar the similar figure to actually calculate the metric module and then go through these steps. Again, the PD that we got was basically kind of an approximate value. If you change the diameter, the other parameters, then the trial pitch might be different. So what you can potentially do is, if for some reason you don't have this material, you can kind of go back and say, hey, you don't want this particular elongation or something of the sort. So I forgot to mention this. If you look at this figure, the 900 is over here. So you can actually look at the elongation over here. So if you recall, we needed 12% elongation at the very least. So if you go here, this is basically about 15% elongation. So we're actually okay with this choice, but if you find the elongation is too small or not good for application, you might need to go back and select a bigger gear which would correspond to a smaller value of PD. So this basically concludes our problem on gear design. Thank you.